So welcome to the fourth part of this lecture 3. Let's just do a recap of what we've done so far. We've looked at some of the basic problems with code. We saw how programs can get arbitrarily large. They can have flaws. Humans make errors, and then computers have faults and failures. They don't perform as they're supposed to perform. Make sure these terms are important, that you understood these terms. They are important for things like the quiz. This part's topic is definitely not going to be on the quiz, but it's just important to see how see examples of problems that have shown up. So we've seen how you can have unintentional program errors, buffer overflows is a very common one, and indeed the very last thing that we looked at, the heartbleed bug, was essentially, it turns out to be a buffer overflow problem. And people think that buffer overflow has been solved. Actually, just the heartbleed bug shows you that no, it hasn't really been solved. You can still run into it. Sure, there are ways to fix it. Okay, you can have incomplete mediation. We talked a little bit about that, more about that later. And then we talked about race conditions. That's when you have multi-threaded code. That would be the most common case. That's also shows up as time of check to time of use errors. You can have countermeasures. The best thing to do is design your software well, make it secure from the ground up, and then test everything. Okay, and then we talked about the heartbleed bug, and we had some background of SSL and TLS. More about this later. You don't have to know any of this for the quiz, really. I mean, you probably should know how encryption works, or the rough idea of how you take some input and then you create an encrypted version of that message. But that's really all you need to be aware of now. So SSL, the heartbleed bug was really not a problem with TLS or SSL. It was just a problem with buffer overflow, actually. All right, so now we'll move on to something a little bit different. This is a little bit more recent. Heartbleed occurred in sometime between 2012 and 2014, so about 4-6 years ago. The drone attack was revealed just a couple of years ago, so March 2016. And it was a problem with actually SSL and TLS. So the vulnerability had to do with old techniques that were not reliable. So at that time, it was thought that about a quarter of the top 1 million domains were vulnerable to this attack. And I'll tell you what DROWN stands for in just a second. It was pretty relevant at the time. 33% of all sites were vulnerable. The problem was that due to misconfiguration, many web servers supported SSL version 2. Remember that SSL is an old kind of technology, and TLS was the replacement for all of these. And so this allowed an attacker to decrypt TLS connections just because a server would support SSL version 2. So the victim client would send a message using a normal modern TLS connection to a server, and the server, for whatever reason, misconfiguration actually, would support SSL v2 when it shouldn't. Why would it do that? Mainly to be backward compatible with clients that used older browsers and older technologies. An attacker can read this TLS connection and then launch a malicious SSL v2 probe to the server and then figure out how to decrypt these communications. So basically what it comes down to is if your server supports these older technologies, SSL v2, then it becomes vulnerable to this drown attack. So a server is vulnerable to drown if it allows both TLS and SSL v2, and a lot of servers did that, including D2L. So the D2L side, it no longer does that, but at the time D2L actually did support SSL v2, and actually for a good long time after that too, mainly because a lot of people who use D2L and uwrf.edu actually used older versions of browsers and technologies and things like that. Okay, so at that time, that's 2016, I believe, 17% of HTTPS servers still allowed SSL v2 connections. However, that was not the only thing. It turns out that if your server actually talked to another server, for example, a database server, and it had a public key that it shared with a different server that allows SSL v2 connections, then if this one server allowed TLS and one supports SSL v2, then the SSL v2 server can be used to attack the TLS server. So you may not support you may not support SSL v2 directly with the client, but if you just so happen to have a shared key with an SSL v2 that is an old server for database or whatever, then this server can be used to launch an attack. So when you take these key reuse problems into account, then an additional roughly 16% at the time of the HTTPS servers were vulnerable to these drown attacks. So that adds up to about a third of all HTTPS servers at the time. So SSL v2, what was the problem there? It used a weak 40-bit RSA encryption scheme. We'll talk about what all these things mean, the 40 bits and the RSA and all of that. And it turns out that this can be brute forced. So this bug allows attackers to obtain a key in about a minute. In 1 minute, they can brute force and find a key that just randomly trying different combinations, get a key in 1 minute. Okay, so what is drown? So drown stands for decrypting RSA with obsolete weakened encryption. So the fact that if you use these old RSA techniques, 40-bit, which is pretty small, then you're basically using a weak encryption scheme and it can be broken. We'll talk about which encryption schemes are broken and which are still good. So this is old. This is a couple of years old, and definitely IIS, that is Microsoft's web server, I forget what IIS stands for, but version 7.0 and 7.5 on Windows Vista, Windows 7, Windows Server 2008, Windows Server 2008 R2. These are all old, but I guess they're probably still in use. They all enabled, so all of these machines with IIS 7 up to 7.5, they enabled SSL v2 by default. There's still quite a few machines that do that. People just don't get around to patching their systems. Also at the time, unpatched Apache, Nginx, Postfix, Red Hat, and Debian systems may also have been vulnerable. These tend to get patched a lot more frequently. It's not that hard to patch these systems. Just have to have people getting around to doing these things. And so once you patch them, these drown attacks were no longer possible. So to protect against a drown attack, server admins have to make sure that these private keys are not used with software that allow an SSL v2 connection. In IIS, what you have to do is just disable SSL v2, and just about most servers that you run into have done that. They no longer use SSL v2 because there's hardly any clients that will use it. There's no reason to have it. So this was a problem with using old encryption schemes that were weak and then could be exploited. So it's kind of hard to say exactly where the error was. It was a decision made by servers to support old technology, which at one point was good. SSL v2 was fine at quite a few years ago, but you definitely wanted to switch over to the newer schemes like TLS. There are problems with TLS versions too. People find these things all the time. Okay, the last thing we're going to look at, the very last thing is actually second last thing, a pair of bugs that showed up very recently, 2017, and they're called Meltdown and Sceptre. Sorry. I think I misspelled this. I think it should be Spectre, not Scepter. Okay, so these were vulnerabilities at the CPU and OS level found in 2017. A spy program could listen and see what the CPU and the OS was doing and detect subtle changes in the way a CPU runs and deduce from that what other programs are doing on the CPU, not anything that's related. And the programs could even be on a separate virtual machine running on the same physical CPU. So it uses this thing called a side channel, that it's not actually reading data directly like we saw in Heartbleed. So in Heartbleed, you were asking the server to fill in a buffer with random data. So you're reading this data directly. That was not what was happening with Meltdown and Sceptre. There, what was happening was you were looking at what the CPU was doing and then sort of deducing what it was doing with other programs. And so this is something that's, it's pretty esoteric. It was actually known in the operating system world that this could happen, but since it didn't involve this direct access of memory, it only involves side channel attacks, people just didn't bother about it. The fix is easy, and it was not extremely alarming to most OS people. The alarming part was that once you do the fix, your CPU slows down because you have to flush a certain part of your cache. And that was actually all you needed, pretty much all you needed to do, and that's it. It fixed the problem, but your system ran slower, and that was the big problem. It affected mainly Intel CPUs, but also ARM chips like the ones that your smartphones have. They were probably vulnerable too. No one really found any attacks in the wild. They just showed that it's possible. AMD's not so much, but then it turns out that a lot of the patches that people sent out caused AMD-based machines to crash. So that was like a side effect of patching these bugs. Okay. Another scarier thing is the Intel management engine. So this was found recently, and it was shown that this management engine is basically a tiny educational operating system. It's based on a tiny educational operating system called Minix that's used in a lot of computer science operating systems courses. And it turns out that Intel was using this open source package, this operating system, in their motherboard chipsets. So this is, you could say it's a level below all of the CPU and all of those permissions. So actually, people call this vulnerabilities at the ring -3 security level. And we'll talk more about what these security rings mean in the context of hardware, but typically what you have older systems, ring 0 was the operating system or the supervisor, and ring +3 was the user processes. So user processes were the sort of, you could say, the least protected, and ring 0 was the most protected. Then you had virtualization, and you needed ring -1, and that was even more secure than operating system code. So that it was like one level below operating systems, and that's why it was called hypervisors. So we'll see more about that later. But these vulnerabilities were called ring -3. That is a super secure sort of state that you should not have any bugs in. If you had bugs in that and someone could attack that, then you have complete control of the entire system. That's the danger of using these things like Intel Management Engine. So these vulnerabilities were actually found last year, 2017. And turns out Google was trying to get rid of these things from their servers, but it turns out it can be re-enabled. So Google has been trying to make their own hardware, but they buy a lot of chips from Intel. Intel had this management engine on their motherboards, so Google ended up with these management engine problems. So as far as we know there aren't any attacks in the wild. People have shown that there are vulnerabilities and that you can actually attack it, but you can be sure that the NSA is on it. All right. The very last thing we want to look at is the web API problems. Specifically, we'll look at OWASP, that is Open Web Application Security Project. It's an organization that works towards improving security for web apps. It publishes the OWASP Top 10, and the last one was in 2017, just about a year ago. And here are the list of vulnerabilities and problems that are known to exist in web apps. This is important because most applications these days are delivered using web apps. So we'll take a look at this list in a lot more detail soon, but if you want to read ahead, definitely look up OWASP Top 10 and you'll see a list of problems. This is just the top 10. There's a lot more problems involved with web apps. Okay.